The purpose of this video is to illustrate an approach to the development of a simple empirical model for the levels of carbon dioxide in the atmosphere since the start of the Industrial Revolution. The combustion of fossil fuels as a source of energy for machines has been the main source of emissions of carbon dioxide to the atmosphere. In this exercise, we will reflect on the climate system, on the processes within it that are operating to release carbon dioxide to the atmosphere, and then to develop a model that describes the evolution of the state of the system over time. Here we will demonstrate that anyone with high school math and who can use a spreadsheet can develop a simple empirical model of the climate system. In this model, we will look at the changes in the levels of carbon dioxide in the atmosphere since the Industrial Revolution. This model will summarise all observed data up to the present and allow prediction of what will happen in the future. We will assume that the Industrial Revolution started in 1800. In the 20 years preceding that date, stationary steam engines were used to pump water out of mines. In the succeeding 20 years, steam locomotives for railways and steamships for ocean voyages were increasingly used. It seems reasonable to infer that there was very little industrial development in 1800. In that year, the level of carbon dioxide in the atmosphere has been measured to be approximately 280 parts per million. Over the last few years, the levels are reported to be in excess of 400 ppm. A spreadsheet is a useful tool in which to develop a mathematical model. The spreadsheet used here to develop the simple empirical model can be downloaded from my cloud folder. In this model, we will use the exponential function. Without going into further detail, this may be considered as a tool to calculate compound interest. The bigger the object, the faster it grows. Before we can develop a model, we must have observed data on which to build the model. Detailed observations on the levels of carbon dioxide in the atmosphere are based on the work of Dr. Charles Keeling. He started recording in 1959, and reliable data are only available since that date. His work is now famous and is called the Keeling curve. It shows an ever-increasing level of carbon dioxide in the atmosphere. The observed levels of carbon dioxide in the atmosphere can be downloaded from the NOAA site. The Keeling curve is an exquisite demonstration of the annual respiration of the planet's vegetation. The cyclic variation in each year shows a decrease in the level of carbon dioxide during the growing season due to the uptake of carbon dioxide from the atmosphere by the growing plants, and an increase in levels during the fall of each year due to decay of vegetation. The data we require can be found in the fourth tab marked Data. The specific data we require is in the file Mauna Loa Annual Mean Data CSV. The header of this file is about copyright etc. and is of little interest to us. Scrolling down, we find the level of carbon dioxide in 1959 was almost 316 parts per million. Scrolling down further, we find that the level of carbon dioxide in 2024 was almost 425 parts per million. We need to copy these data into the spreadsheet in which we will develop our model. The observed data are in columns A and B of the spreadsheet. For the present, please ignore any other data displayed on the spreadsheet. Although we wish to develop a model starting in 1800, it should be noted that reliable observed data is only available for the most recent 65 years in column A and B. These observed levels of carbon dioxide in the atmosphere are shown as blue dots in the top graph of the spreadsheet. Ignore the red line for the present. Clearly, the levels of the carbon dioxide are increasing year on year, and the rate is itself increasing with time. This is highly suggested that the emissions of carbon dioxide to the atmosphere from the ever-increasing combustion of fossil fuels is increasing in an exponential manner. Now we look at the development of a simple model for carbon dioxide in the atmosphere. As already discussed, we need to build a model from the beginning of the Industrial Revolution, about 1800, to sometime in the future, let's say 2043. We do not wish to overestimate our ability to predict the future. The model that we will build in the spreadsheet starts with column D. The model year is shown in column D, starting in 1800 and increasing by 1 each row down the table. Next, we copy the carbon dioxide level data from column B to the appropriate row of column E, where these data will be used in the model. The equation suggested is as follows. It contains 3 parameters. CO2 in year 0 is the level of carbon dioxide in year 1. Rf is the proportionality constant, and K is the exponential rate constant. K is defined as the natural log of 2 divided by the half-life. These parameters control how the model evolves over time. There is only one variable in the equation, t, the time since the start of the model. Rate constant. The values of these 3 parameters are contained in the first 4 rows of column F in the spreadsheet, specifically F1, F2 and F3. The value of K may be readily calculated from the half-life. For many people, the exponential rate constant K is a rather abstract concept. For this reason, the exponential rate constant K is not altered directly. Rather, it is calculated from the half-life, whose value is stored in cell F4. The level of carbon dioxide predicted by the model are shown in column F, from cell F9 down. Ignore for the present how the model works. That will be explained momentarily. In the graph, the model output is shown as a red line. It is clear that in this initial guesstimate there is little agreement between the observed data, the blue line, and the model data, red line. However, this disagreement gives us a clue as to how we might find good agreement between the datasets. It is obvious that the observed data for each year and the calculated data from the model for that year must be as low as possible. Each year must be involved in calculating the goodness of fit. Statistically, this is achieved by finding the difference between the observed value and the calculated value for each year. This difference is then squared. Finally, a sum is taken of all these squares, and this number is called the residual sum of squares. The best fit model will be the one with the lowest residual sum of squares. We must now look at the structure of the model in more detail. Next, we must look at the equation and translate this equation into a formula suitable for a spreadsheet. The value of CO2 0 is copied into cell F9. The spreadsheet formula for the model is then copied into cell F10. Each individual set of parameters result in a specific model. However, we must alter the parameters one at a time, looking at the residual sum of squares in H5 to see that they're getting a lower value. We start by changing the half-life to 50, where the residual sum of squares is almost 500,000. Next, we change the half-life to 40, where we get a better residual sum of squares of 399,000. Next, we change the half-life to 30, where our residual sum of squares is 129,000. Then we change the half-life to 28 years, where the residual sum of squares is 42,000. Next, we change the carbon dioxide level in year 0 to 280 and get a residual sum of squares of 22,000. Next, we change the carbon dioxide in the initial carbon dioxide to 285 to get a residual sum of squares of 12,000. Next, we change the carbon dioxide initially to 289 and get a residual sum of squares of 6,200. Notice that the residual sum of squares is decreasing as we progress through these iterations. Next, we change the response factor to 0.6 and the residual sum of squares falls to 1,600. Next, we change the initial carbon dioxide down to 285 with a residual sum of squares of 870. Next, we increase the half-life to 28.5 years and the residual sum of squares jumps to 3,300. Going back to initial carbon dioxide of 288, the residual sum of squares is 1,200. Next, we guess that the half-life is 28.5 years. The residual sum of squares falls to 474. Setting the initial carbon dioxide to 288.5, the residual sum of squares goes to 397. Setting the initial carbon dioxide to 288.45, the residual sum of squares jumps to 403. Therefore, we revert to the previous value. We'll take that as the best fit that we can find. So the three parameters for the model are initial carbon dioxide equal to 288.5, the response factor equal to 0.62, the half-life equal to 28.5. We observe that this model is a good fit. Note that I am not saying the best fit between the observed and model data, and we can explore what the model predicts for the future. The data here implies that we only have agreement for a little over 2 half-lives. Now we must look at the outputs from the model. We know that the level of carbon dioxide for 1800 was 288.5 parts per million. At the end of our model here, we have a level of carbon dioxide in 2043 of 511 parts per million. This is not quite double what it was in 1800 at 288.5 ppm. We will extend our model further by copying the contents of row 252 down a few more rows. Let's say down to the year 2061. Note that the model predicts that the level of carbon dioxide doubles between 1800 and 2054. We will discuss the importance of a doubling of the level of carbon dioxide in the next few slides. If we look at the full-time span for which the model predicts, the red line, and the observed data, we are reasonably certain that the model is a valid one. By implications, this process has operated for 7 half-lives. Whatever the nature of the process, it is highly unlikely that an exponential process that has been operating for over 7 half-lives will suddenly change. It seems reasonable to assume that the process will continue to operate as heretofore for at least another half-life or more. In 1896, Svante Arrhenius calculated that a doubling of the levels of carbon dioxide in the atmosphere would result in an increase of temperature of 5 degrees centigrade. This was without the benefits or assistance of computers in his calculations. With a level of 288.5 ppm in 1800, the level of carbon dioxide in the atmosphere in 2054 would be increased to 597 ppm, and thus the temperature would be 5 degrees centigrade warmer than in 1800. He estimated that it would take humans thousands of years to release that much carbon dioxide. Next, according to the IPCC report AR6, the equilibrium climate sensitivity is likely to be between 2 degrees and 5 degrees, with a high likelihood of it being between 2.5 and 4, and the best estimate that they propose is 2.9 degrees centigrade. By that criteria, the temperature in 2046 would be 2.9 degrees higher than it was in 1800. In the last few months, Dr. James Hansen and his colleagues estimated the climate sensitivity for a doubling of carbon dioxide to be approximately 4.5 degrees centigrade with a high degree of probability. This is supported by multiple lines of evidence. This means that a doubling of carbon dioxide levels between 1800 and 2045 would lead to an increase of temperature in 2045 of 4.5 degrees centigrade. Whatever the differences between these proposed climate sensitivities, we will only have to wait 20 to 30 years to see which, if any, of these predictions are correct. In the next video, we will prepare a simple empirical model of the climate system using temperature as the property of the climate system to measure the state of the system.